And here we are again for another Astronomy Daily Live. So, hey everybody, hope everybody's doing well. Come on into the circle of friends who share a common passion for the science of astronomy. I'm going to tweet the fact that I am live. So, come on in, everyone. Join the circle. For those of you who are watching this later, howdy, howdy, howdy. Hope the future is well. The past looks pretty good. Past looks pretty good. So no major complaints. It's still, the sun is still setting here in southeastern Arizona in the United States, just going down. We've got another month. We've got another month until the solstice. In the northern hemisphere, of course, that's the summer solstice. And in the southern hemisphere, that's the winter solstice. So everybody in Australia, South America, getting a little chilly, I think, down there. While up here, we're getting, up here in the north, we're getting pretty nice and warm. Pretty nice and warm. I actually sort of consider the solstices and the equinoxes to sort of be mid-season things. So I sort of see June 21st as not necessarily the beginning of summer, but the middle of summer. And likewise with, September 20th is sort of mid-fall, and December 21st is midwinter, and March 20th, March 21st as being mid-spring. So that's just those designations are sort of arbitrary. So call it whatever you want, but that's one of the cool things that all of humanity shares. Okay, we don't share the same cultural um, um, holidays, right? But it's a fact. It's a fact that for everyone, on June 21st at 10:07 UTC, the sun will reach its highest declination in the sky for this year. And that goes for everyone. It doesn't matter where you are, what you think, how old you are, um, nothing, nothing at all. And um, when it's time for the equinox, the declination of the sun is exactly 0 degrees, no matter who you are, no matter where you are. And it happens at a moment in time, right? It's an actual, uh, you know, it's just one of those nows, right? So there really is no duration, right? It just happens, and that's it, right? Just for that moment. I think they call the smallest amount of time that we apparently can be aware of. And we haven't. I don't think we've been able to measure these kinds of things yet. But the mathematics says that the shortest uh, duration that is possible with the sort of physics that we understand at this time is what's called the Planck time, and that's something like 10 to the negative 43rd seconds or so. It's a very, very, very short um, duration, very, very short. There's also a Planck length, which is the distance that a particle of light can travel in a Planck time, and that's something like I want to say 10 to the minus 30, 34th, 10 to the minus 36th meters or so. I'm going to pull up my chat here, see if everybody's gabbing away. Bobby is there. Hey there, Bobby. Tom is there. Hey, nice to see you, Tom. Saw your tweets about the Whirlpool Galaxy and being able to yeah, I just sort of read your tweet on it saying that it was observed both in the visible and the X-ray. So I'll have to look at that a little bit more, which I certainly will do. Everybody's all excited about this asteroid that was just discovered that uh, um, apparently has a 1-to-1 um, ratio retrograde motion with Jupiter, and it turns out that it's a little weird looking. I'm trying to investigate this a little bit more. I found one paper um, from Friday. I think it was from Friday that, or maybe it was yesterday. Um, don't remember. Um, that talked about this asteroid, and they it's kind of an interesting, pretty mathematical paper, sort of explaining reverse retrograde motion, and that looks intriguing enough that I'm definitely going to take a look at that probably after this live stream, and see what's going on there. But yeah, everybody seems to be excited about this asteroid that apparently is may not be part of our solar system. I yeah I haven't gathered enough information yet to be able to think or say much about that at all yet. But yeah, how these things go, right? Is that there's always something interesting going on in the astronomical world, and fact of the matter is that folks, we have not seen anything yet. We thought for you know quite a while that there really isn't anything too much going on in the universe, right? And you know when I sort of heard those kinds of things as a kid, right? That the stars are steady and once in a while you'll see like a supernova, um, but even those are a little bit rare, and all of that, right? And I just had to look at pictures of the sun and seeing how active and dynamic on a minute by minute, right, second by second, um, uh, uh, thing, that it's like, well, you know, and look, just look at the weather on the Earth, right? I mean, it is changing moment to moment, right? And so, why would anybody think that it's different anywhere else, right? So, and as we um, are able to sort of observe the universe in this thing called the temporal domain, right? Looking at time domain um, activity, yeah, things are happening uh, at an unimaginable pace, and yeah, that was very much underlined. I forget what where I was reading this, but the LSST, the Large Synoptic Survey Telescope, is apparently going to be probably putting out millions of um, alerts every single day for on something happening that it sees, right? These um, uh, these events, and so yeah, it's a very 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 active universe, just like just like we're active, right? Just like everything on this planet is extremely active, right? Operating on different time scales, though, right? So you know, um, ocean waves, right, have sort of a cadence, and you know, everything, you know, operates at, you know, one or more cadences, from extremely fast to extremely slow, right? You know, your breathing, your heartbeat, even uh, um, brain patterns and all that. You know, they seem to run at, you know, sort of periodic and sometimes chaotic uh, uh, ways, and so yeah, and you know, I mean, we've barely um, begun to sort of scratch that surface, and yeah, I mean, we're uh, the uh, the next 10 or 20 years in terms of astronomy and science in general, um, I think is going to be pretty mind blowing. I think we're going to finally realize that in um, in many ways our interpretations of what we're observing have just been, like, you know, totally wrong, right? Observations are valid, right? But what we think is going on um, probably isn't, and that's you know, to think that we you know have have an understanding, and, you know, sort of the science is settled on certain things. Nah, that that I mean, as a scientist, for me, that throws up a red flag. It's like, no. I don't think so. I don't think so. I mean, I think the harder we look and the more we look, probably the more mysteries we're going to find, and that's sort of how this seems to be um, set up, right? Told you before. Um, 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 Alan Watts, um, in one of his lectures, he's he's talking about, you know, sort of imagining ourselves as this being that has access to all these buttons, right? And each of these buttons um, is like a different experience, right? So push the button, and you know, uh, um, you have a particular life experience, and you come back, push another one, and you have another, you know, and there's one button, right? There's one button that's marked surprise, right? And we have all pushed that button, and poof, here we are. So yeah, I think it's just going to be surprise after surprise, and you know, I mean, we um, history shows that we've always been pretty sure about what we think we know is going on, right? And history also shows that we're usually, you know, pretty wrong about that. So I don't see any reason why things are going to change We're, I mean, we're really not any more sophisticated um, than what we were, thousands of years ago. I mean, we we might be able to, manipulate matter a little bit more. But yeah, I sense we have a long ways to go on that. We may never, right? I mean, if we ever do come up with answers, the actual real answers, and it's like, well, what? I mean, what else is there then, right? Sounds pretty boring. So cheers. I think we'll always be able to figure out or find new and interesting things, and uh, yeah, I I don't even think that we can possibly imagine um, what things are going to be like. It's just impossible. It's impossible. So, and that's you know for me, that's just how I want it. Just how I want it. So very, very cool. So hope everybody's doing well. The sun has now set. Yeah, it's going to be another nice evening. Get out there and take a look at the moon tonight. I was over at cloudynights.com. I'm going to go over there, cloudynights.com. Let me share my screen here too. Let's see. For some reason, that's there. Hopefully, I didn't kill it. Yay, I didn't. Ah, this poor little machine. Hard. All right, sharing the screen, going over to Cloudy Nights. I'm going to go over to the. So, about cloudynights.com. I definitely encourage you to get over there and check them out. Found. Who knows what that is? It's thing. But yeah, I was looking at the celestial calendar, which we we went through, I think, on like May 1st or May 2nd. So those of you who didn't see that, you can sort of go back and see what's going on there. So sorry for the dropouts with the video goes sometimes. Whoops. For today, right? Today is, well, technically right now, right? It's 2:18 UTC on the 22nd of of May, and so right now the moon is very, very close to the star Regulus, and that's the bright star in Leo. So yeah, go out and take a look at that. That's always extremely cool. The northern hemisphere is experience their autumnal um, equinox in about 40 minutes. Well, happy equinox on Mars. Wow, that's very cool. Very, very, very cool. Let's see what else. The lunar X is visible. Blah. Yeah, I'm still dropping out a little bit. Sorry about that. Um, for some reason, Norton is doing something. So I'm going to just X Norton out and hope that my laptop doesn't get eaten by the monsters. So yeah, definitely go out and take a look at the moon like right now, right? Because I mean, it's sort of at its closest to Regulus as we speak. So yeah, check them, check that out. I really like cloudy nights. Oh, I guess I have to sign in. That sort of sucks. Let's see. I think I'm Cosmic Lettuce on that. If I remember right. Let's see. So this is a uh, active forum. We can we can go over here that says view new content, and you will see that. Let's update this. Well, we really don't have to. You can see this is my local time, right? So I'm 7 hours behind UTC. So right now it's 7:21 p.m. UTC, and you can see in the past 5 minutes, right? There's been what eight new posts. So it's a very active group, which is very cool. Um, let's see if there's anything interesting. So here's somebody that took a 6.7 hour exposure of M101. Let's take a look at that. Hello, cloudy night. After a year plus of no imaging due to gear problems, second baby, and absolute shit weather, I finally have something to show. So this was taken north of Montreal in April. I assume that means Canada. So not bad. Too bad. And then lots of comments and stuff too. It's really great. This is a great site. Awesome site. So if you're into astrophotography and have any kinds of questions about how to get into that, um, you will have all your questions answered at this site. Got a lot of experience here, for sure, for sure. Let's look at Jupiter through a Questar 3.5. I assume that's like a 3.5 inch. That's pretty good. Couple of moons over here too. Let's see, is there a zoomed in? I guess that's it. Yeah. Okay. What else has he got? Oh, that's nice. Look at these crazy storms. That's insane. Yeah, that's crazy. And it's really amazing how it changes. I mean, you can see changes, mm, you know, almost moment to moment. Very cool. What else do we got here? Abysmal guiding. 17.5 inch binoscope build. M104. That's a fantastic galaxy to observe if you haven't yet. Apparently these people haven't. Let's see. Let's update this and see how many new ones we have. BSC Air, Jupiter, April 11th. Take a look at that. Seeing it had been so poor during early April, I had nothing to post. These images are just barely above nothing, but I'm tired of processing and tossing. Cool. Let's take a look at these terrible images. Yeah, okay. Well, that's definitely not great, but yeah, it's Jupiter. So yeah, it looks like these are taken with some different filters, right? This sort of pulls out the methane CH4, right? So wherever it's bright here, supposedly there's a lot of methane, and where it's dark, there isn't. So that's probably the red spot there. And look at that, there's a lot of methane in there. Now, UV, I'm sort of assuming is like some kind of ultraviolet light. I'm not quite sure. But again, um, uh, yeah, it's kind of interesting, isn't it, that the red spot is sort of dark in the ultraviolet. Oh, it's from Surprise, Arizona. Okay, well, I know where Surprise is. Paul Maxton. Wow, that rings a bell. That name rings a bell. And Surprise is up up to my north. Pretty much everything is up to my north. I'm pretty south. Um, so that's pretty cool. I'm kind of interested in seeing where he's located. Send a camera and sensor pack spacecraft directly into it. Yeah, yeah. We will eventually. Let's see if there's anything else interesting here. How do we understand quantum mechanics? Question about crop sensor cameras and lenses. Hmm. Crop sensor cameras? Not quite sure what a crop sensor camera is. I'll have to investigate that a little bit if I get a chance. What else? What else we got here? Taking a little bit easy tonight, just being really casual, not getting too much in anything. I said I did some analysis of the words used uh, in both my live stream and uh, the weekly space hangout, and found that um, they were throwing about 3 words a second out, and that's a pretty astonishing rate, right? So I've have sort of dedicated myself to speaking a little bit slower. And if I measure mine from a couple of days ago, yeah, I'm doing about 1.7 words per second. Um, so yeah, definitely a lot slower, and that's that's just what I sort of prefer, right? These fast talkers, I can't. It's hard to keep up with them. I think I just have a slow brain. That's all. Just a slow brain. I don't mind. Cheers. Well, I think that we should dare to try to do a constellation of the day. I'm going to stop sharing here just for a second. Yeah. So I think we should dare to do a constellation of the day. Now, I have absolutely no prejudice whatsoever, right? But I do notice things, right? I can't help it, right? And I've been doing constellation of the day. I think this might be the 6th or 7th one. I forget. And every single one so far, except one of them, has been a constellation in the southern hemisphere. And as I said, I mean, I don't have any kind of prejudice or anything. I don't care, right? I don't care. But it's sort of like flipping a coin and getting heads 5 out of 6 times. It's like, really, really. So let's try it again. I'm really curious to the constellations. I I haven't done this kind of analysis, right? But I'm thinking that the 88 constellations that are defined by the International Astronomical Union, right, are more or less evenly distributed over the celestial sphere. It depends on the size of the constellation, um, and all that. But I sort of think that maybe there's a relatively even distribution. Now, I could be totally wrong, and yeah, I should look at that. And it'd be relatively easy to work out sort of the area of the sky covered by each of the constellations, and see if there are more constellations in the southern hemisphere as opposed to the northern. Um, yeah, I don't know. It's an interesting question, I guess. Um, but I guess I sort of have to assume that it's a pretty even distribution, right? So the International Astronomical Union has determined that there are 88 constellations in the sky, right? 88 of them. And so what I can do is I can pull up an alphabetical list of all 88 constellations, right? And then I can go over to random.org and have this random number generator choose an integer between 1 and 88, and then I will determine which constellation that is in this alphabetical list. Okay, so let's just go do that. So I'm going to share my screen again. We're going to go to infinity. Yay. I love going to infinity. That's my favorite place. So let's go to random.org. And it's going to have me choose, or it's going to choose a number between 1 and 88. And I'm dying to push this button because I want to know if it's going to be another southern constellation or a northern constellation. I don't know. All right, you ready? Okay, here we go. Drum roll. Number 85. Okay, so I'm going to go to my list of 88 constellations and I'm going to go down to the 85th one. Jeez. All right, it is the constellation Vela, Vela. And where do you think Vela is? Honestly, I don't know. I definitely don't know all the constellations, right? Some of them are a little obscure, right? Jeez. Oh man, look at that. Can you believe it? The constellation of Vela is in the southern hemisphere. Wow. Wow, that is I'm beginning to sort of think that maybe there are more constellations in the south because it's just a little too much for me to handle this idea that we've just randomly picked uh, what 5 out of 6 or 6 out of 7 constellations, and they're all only visible in the southern hemisphere. That's just mind blowing. That's crazy. Absolutely crazy. Let's take a look at Vela here. So it's it's pretty small. It looks like a pretty small constellation, but it's got some pretty bright stars, quite a few also. So let's see. So it's going from a right ascension of around 8 hours over to about 11 hours or so. So yeah, this constellation, in the early evenings, right, is actually visible right now. Yeah, even I would be able to see because I'm at a latitude of about positive 32 degrees or so. So yeah, I mean 32 minus 90. If I grab my handy dandy calculator here, 32 minus 90. So I can see down to a declination of about negative 58. So I can actually see this entire constellation, right? Because it's going down to about negative 56, negative 57 or so. And then all the way up to what, about negative maybe 38 or so, something like that. So technically, from my latitude, at least, I can see this entire constellation, and yeah, I should probably try to check that out. It looks like it's right next door to Centaurus, and I know that I can see at least some or all of Centaurus because I can see the big um, globular cluster over there called Omega Centauri, which is indeed a sight to see. It is massive. It's massive and amazing. Yeah, very very amazing. But yeah, let's stick to Vela. Quite a few quite a few stars. They draw the lines here between the stars that sort of make up the asterism that is supposed to be this constellation. What do they say that it is? What it's supposed to be? Uh, let's see. Let's go back here. Let's go back one more. Oh, too far. Okay, its name is Latin for the sails of a ship. So it was originally part of a larger constellation, and it was divided into 3 parts. Oh, that's kind of cool. That's kind of cool. So this is the sail of a ship. Okay, that's 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 fine. Can accept that, I suppose. Yeah. All right. So very very cool. The usually how these constellations go is that the brightest visible star is named Alpha, and then the next one is named Beta, and then Delta, and then Gamma, or Gamma Delta. I don't know my Greek alphabet, I guess that well, but in this case, maybe because it was split up something like that. Don't know, but it looks like the brightest one might be, I think that's, is that Gamma? Gamma, there's Delta, there's Lambda, there's Kappa, there's Mu, there's Psi, and there's, I think that's Phi, right? The O with the line through it, something like that. Yeah. So yeah, doesn't really follow the rules per se. Uh, Rules are arbitrary. So okay, so a quick count, Tom. There's 36 constellations in the northern and 52 in the southern. Okay, so we're twice, almost twice as likely, not quite, right? What is that? 52 divided by 36. Whoops, 52 divided by 36. So we're 1.4 times more likely to randomly choose a southern hemisphere constellation than a northern hemisphere constellation. Well, that still doesn't explain why I think out of the out of the 5 or 6 or 7 of these that we've done so far, there's only been one. There's only been one in the north. So yeah, I think the universe has some kind of prejudice. I certainly don't. So it looks like there's maybe a couple interesting objects here. Let's look at the Wikipedia page, but I want to go over to Burnham's. That's my source. Oh, come on now. Let's see if there's anything particularly interesting here. Brightest star is Gamma. It's a complex multiple star system. Okay. So that might be interesting to look into. Gamma Velorum, should we? Let's do it. So let's go over to Simbad. And search for Gamma Velorum. Velorum. It's also a Wolf Rhea star. I'm trying to remember exactly what a Wolf Rhea star is. I think it's one of those crazy massive. I gotta say that if I were a kid today with something like Google, man, I don't I don't think I would ever be seen. Red star. Yeah, they're just very massive. Okay, so they're evolved massive stars. Okay. All right. Well, very cool. Anyway, so yeah, let's take a look at this bad boy. See what's so exciting about this guy. They said it was a multiple system, and that sort of got me interested. So let's take a look here. So let's see the celestial coordinates: 8 hours, 9 minutes, 31.9 seconds, right ascension, and a declination of negative 47 degrees, 20 minutes, 11.7 seconds. Okay. Pretty close to the galactic equator, right? Just 7 degrees south of the galactic equator. So in a pretty rich, I mean, that's going to be a pretty rich field of stars. Looks like we and it are sort of mutually moving away from one another at around 15 kilometers per second. So that's not, in the grand scheme of things, I don't think that's incredibly fast. So we're more or less moving together. Um, and yeah, the spectral type is WC8. Wow. So yeah, that's a that's a massive monster. So here's all the magnitudes, right? This is how bright this object is using different filters, right? UBVRI, JH, and K. These are sort of the standard, um, what are called the Johnson filter set. So U is sort of violet colored. B is blue. V is visible, which is around the green, like around 5,500 angstroms or so. R is leaning towards like hydrogen alpha, which is about 6,800 angstroms. I, J, H, and K are moving into the infrared. So you can see that it's brightest. It sort of gets brighter as you move towards the blue and the ultraviolet. All right, so that's kind of interesting. Wow, look at all those different names. So this one star or star system has all these different names, right? Wow, that's pretty crazy. Lots of references. Okay, well, that's a good thing. We can get back to that. Let's see. Let's look at the measurements. Looks like we have a distance measurement here, a couple of velocity measurements. So 157 parsecs. So a parsec is 3.26 light years. So it's hard to do this with one hand. 3.26 times 157. So they're saying it's like 512 light years away. So yeah, that's pretty darn close. Pretty darn close. And that sort of explains why it's as bright as it is, right? Um, Interesting discrepancy between the measurements of the velocities, right? We're going from 12 up to 35. Wow. Here's the proper motion, which, excuse me, I think I interpret as the number of arc seconds per year. So it's moving in a negative right ascension way. So it's moving west, and it's moving in a positive declination way. So it's moving north. So it's moving towards the northwest. Um, wow, at a pretty good clip. I mean, that also, the fact that we can see it moving, over relatively short time scales also indicates that it's pretty close as well. So let's see. Let's look at these observations here. Oh, where are they? Here they are. Let's see. Don't know what these are going to be. Let's take a look at them anyway. Curiosity. This live stream is about satisfying curiosity. Okay, so these are like some spectra taken in sort of different bands, right? And don't exactly know what the units are here, but want to say, as they're talking about infrared, the Infrared Space Observatory, my guess is that these are in microns. So I don't know if you can see those numbers or not, but this is saying 2.38 to 2.6, and then 2.6 to 3.02, 3.02. So yeah, these little steps, and it goes all the way up to um, almost 30, and then this bottom one has the whole thing. So that's pretty cool. That's pretty cool. Kind of neat that they're doing that for us. I know that's pretty hard to see. It's hard for me to see them. So yeah, I'm sure it's probably a little bit hard for you to see it too. Let's see. Go back here. Let's see what else. So these spectra indicate that there are these emission lines. These are real things, real um, material, like either elements or molecules that are being excited in some way, and they glow, and that's called an emission. Sometimes you'll see these little dips here like that. It's called an absorption. So that's that's when these same elements or molecules are actually absorbing light, and so you'll even um, you'll usually either see emission lines like that or absorption lines like that, depending on what is going on, right? And that seeing emission lines or absorption lines can actually tell us a little bit about what's going on. So that's cool. So these are just more spectra, thermal infrared spectra. So we're actually looking at the heat here, right? The actual heat from this star. All right. Well, let's dive into the references, because the thing that made me interested in this was the fact that it was like a multiple star system, and I'd like to sort of see if we can find a paper about that. Colliding wind binaries. All right, hold on. I have to perform my kitty duty. Hold on one sec. We humans are mere servants to the feline master race. Let's see. I wonder if we can do a search for gamma. There we go. 3D magnetohydrodynamic models of non-thermal photon emission in the binary system, gamma 2 Velorum. The Gaia ESO survey, lithium depletion in the gamma Velorum cluster. Okay, interesting. Membership and initial mass function of the gamma Velorum cluster. That looks interesting. N-body modeling. Kinematic structure. That's just how things are moving, right? The outer wind of gamma Velorum. Well, this one back here, the one membership and initial mass function. Let's just look at that one really quick. Go over to the astrophysics data system and see if we've got a paper. Oh, they sort of changed their format. Always have to change their formats, you know? So let's do this. Yeah, I didn't think that was going to work. Data products. You know, they've changed their format around a little bit. It's turkeys. Let's see if this works. Nope. See how they are. Let's I don't give up that easily though. Pretty stubborn when it comes to trying to find things. They looks like ADS has changed their links around a little bit, so it's making it even harder for us to find things. There it is. What's so hard about that, ADS? Come on, guys and gals over there. Fix your links. Gee whiz. All right, let's see what this is saying. Understanding the properties of young open clusters, such as the initial mass function. That's just, you know, how much stuff is there at the beginning, right? Star formation history and dynamic evolution is crucial to obtain reliable theoretical predictions of the mechanisms involved in the star formation process. So we want to obtain a list as complete as possible of confirmed members of the young open cluster Gamma Velorum with the aim of deriving general cluster properties such as the initial mass function. Okay. So they're saying that these are like 5 to 10 million years old. So yeah, they're very, very young, but very, very big. Very, very big. The most massive member is Gamma 2, which is a binary system, 9 solar masses in size, and an O star that's 30 solar masses in size. So yeah, some pretty massive stars here. 30 times the mass of the sun. That's 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 pretty big. Of course, what I always want to try to find as soon as possible is some pictures. But yeah, we'll see. We'll see. Let's see what it says here. Was first observed in. Okay, so that's just their observations, I guess. Uh, homogeneous overview of the kinematic and chemical abundance distributions. So 1,242 targets observed with this instrument that they're calling Giraffe. Giraffe. Uh, where is Giraffe mentioned? No, we're going to have to look up the reference if we want to know what giraffe is. These papers are really, really great, you know, I mean, in terms of tangents, right? You know, I mean, you can pick any paper and be like, what is giraffe, right? And you can go that way, right? And you can get completely lost, right? And it's like, oh, you know, after a couple hours or so, it's like, oh, where am I? To establish the membership of the cluster, starting from an inclusive sample of candidate cluster members. Membership will be confirmed or rejected by using radial velocities and stellar properties. You know, the idea with clusters, at least the theory goes, is that all these stars formed at the same time with basically the same kind of material, right? The same kind of stuff. So, you know, if you find a star that's made of you know, really radically different stuff than sort of everyone else, then it's like, oh, okay, that may not be a member of the cluster. Yeah, so, you know, how they move, they all, you know, and that's also the theory too, right? Is that if they all formed at the same time and basically in the same place, then early on like this, they're all going to be moving sort of in the same way, right? They're all going to be moving with a particular speed and a particular direction, right? So let's see, dedicated to the dynamical analysis of this cluster using the very precise radial velocities. So you can measure radial velocities by looking at those spectral lines and supposedly measuring their either redshift or blue shift, right? So you know, just as a rough example, and this isn't what it actually is, right? But I mean, if if in the laboratory here on Earth we uh, we make um, some measurements of like hydrogen, right? And we see the hydrogen lines in the spectra, and those lines are at a particular place, right? Um, some wavelength, right? Wavelength X, right? Then, if we look at these stars, right, and look at the spectra, see the hydrogen lines, we know that they're hydrogen lines, but they're not quite in the same place as those in the lab. And it's like, well, what's going on there? Well, the explanation that is given, and it's probably pretty valid, right, is that it's some kind of Doppler shift, right? Either blue shifting or red shifting, depending on the star's motion, right? I mean, it's just like a passing train, you know, um, blows a whistle, and you know you hear the change in the pitch. Well, pitch change in pitch uh, is just like change in color, right? So yeah, they're able to measure these with extremely high resolution spectrographs. They can actually measure, you know, how much of a shift it is, and then say, oh, okay, well, that object has to be moving um, a certain speed, either towards us or um, or away from us. So what I'm going to do, what I should do is I want to go um, to the Gaia data release 2 and pick up these stars as well. So this is just a basic color magnitude diagram. So they have these um, photometric measurements at two different wavelengths, right? The V and the I. And then what they've done is they've taken those magnitudes and they've subtracted I from V, and then they've compared that to just V. So you get these interesting structures, right? These interesting structures. And so they've picked out 1,242 targets. Let's see, the empty red squares are the candidate members. The black filled circles are X-ray detected objects, and these lines are lines that are created by models that say, okay, uh, stars that have this age, right, 20 million years, will lie along this line, and stars that are 500,000 years will lie along this line. So there's an inference here, right, that says, okay, it looks like all the stars between these two lines are therefore between 500,000 years old and 20 million. So yeah, okay, that's looks like a reasonable conclusion. So yeah. Let's see, radial velocity membership. Yep, yep, yep. So this looks like a histogram of radial velocities. Yeah. So this is um, well, I mean the way that I'm going to interpret this without diving into the paper totally is that this is showing sort of the number of stars that have a certain velocity, right? So kilometers per second, and you can see this spike, right? That means that a lot of stars have that very very narrow um, velocity. And I wish PDF. I don't know what PDF stands for. Quarter of a kilometer per second bin. Yeah, I'm not quite sure what those units are, but I think we can sort of go back to, this. This is the number of stars. So this is just a zoomed in version of this, right? You can sort of see here it's going between negative something and 150. Here it's going between 5 and 30. So it's just this little region right here that they're sort of zooming in on. And it looks like they've got their actual counts, which are these step lines here, and then they've overlaid that with obviously some kind of a model of some sort. So that's pretty cool. Looks like there's quite a few stars that share pretty much the same velocity. There's this interesting little shoulder here that they probably talk about. Huh, okay. Wow, that's a pretty complicated little graph. It's some kind of color versus something to do with lithium. Yeah, I guess we'd have to dive into the paper to see exactly what's going on there. Some pretty interesting structures. What I really like to see in papers, and we really don't see this enough. You see these things? There's a little almost impossible to see dot right in the middle, and then there's these lines, these vertical lines and these horizontal lines. These uh, these are showing the measurement errors, right? So they made a measurement and it's like, okay, that's where it is, but this is how certain we are in terms of that value. So that value could actually be anywhere between those two lines. So some of them are really, really nice and small, uh, which means uh, very good accuracy. And some of them are very, very wide, like this one. There's a big one over here. Um, so yeah, the accuracy just isn't quite as good. So EW. I'm really kind of curious to know what EW stands for. When you find something like that in these papers, you can usually backtrack, right? And the first time that it's used, though it usually says, it at least gives you um, what the acronym is. I'm not seeing any more EDU. There's what PDF is, probability density function. So yeah, that's just a count. But the first instance of EWLI is talking about the lithium line. In this section, we assign cluster membership on the basis of the strength of the lithium-1 6708 angstrom line. This is a well-known age indicator for young stars, such as those expected to be found in the gamma Velorum cluster. Um, It still doesn't tell me what EW is though, so I have absolutely no idea. It's some kind of line intensity, something like that. So yeah, line intensity, line strength, hard to know. I'm guessing there. Um, Interesting structure though. Interesting. Interesting. Huh. Don't know what it means. The function of color for all targets observed in the gamma Velorum region. Red empty circles are candidate cluster members selected from the lithium line criterion, whereas blue crosses are the 64 objects which are left undefined according to the lithium test. So apparently these red guys are uh, cluster members according to this test. And I guess the blue guys and the black ones are not. Okay. So it looks like to be a candidate, you have to have a certain amount of lithium, right? Either this or more. Um, but that's not necessarily true because it also looks like you have to have a certain color, right? A certain V minus I. So okay, kind of cool. Wow. So this is a really long paper. Final list of members. Cool. Yeah, I think I'm gonna go over onto Gaia and track these down. And again, it always just blows my mind how much work is put into this and how much consideration and thought goes into these kinds of things. It's very humbling. Um, it's so much effort is put into this stuff. So they've derived masses. See, what do they say here? "246 confirmed members." 246 members. That's a nice little cluster. Very cool. Okay, so here's a list of all of them. All 246 members. Scientists love publishing tables. They've got their masses over here. Cool. Masses in terms of solar masses. So yeah, some of these are pretty tiny. 1/10 of a solar mass. If there's any big ones. There's 1.2, 1.05. Oh, I think there's 1.3. So not really any big stars here at all. Not, at least not the ones that I saw that they're claiming to be members of this cluster. Pretty small stars. Very cool though. Looks like they did a pretty thorough job. You can also see, these are the magnitudes, the V magnitudes. Most of these are really faint, right? 18th magnitude. Here's a 13th one. Okay, that's sort of bright. I saw a 12, but look at all these guys. They're like 18th magnitude, 17th, 16. Yeah, pretty darn faint. Pretty darn faint. So very cool. Very cool. Well, we didn't get much into the constellation of Vela itself, but we did look at one of the stars in Vela. Looks like there's some pretty interesting looking non-stellar objects in there too, so-called deep sky objects. Um, Planetary nebula, the egg burst. Yeah, very cool. There's a Herbig-Haro object. Those are very strange and interesting. NGC 2670. NGC 3201, a globular. Yeah. Well, very cool. All right. Well, as I said, tonight's just an unusually nice and casual, slow live stream. Taking it easy, not going too deep, just having a blast, right? Just going wow, and seeing what's around, getting to know a constellation that at least up, those of us in the north here will never see. so all right. Well, I'm gonna get out of here for tonight. Hope everybody has a great evening, a great day. And yeah, I'll see you again in a little less than 23 hours on the spin. Don't get dizzy. Don't get dizzy. It's a smooth ride. So enjoy. And yeah, I will see you again tomorrow. Okay, bye.